How's it going, ladies and gentlemen? Mr. Donnie here again. This time, taking a look at 19.1, spontaneous reactions. So our objectives are as follows. We want to be able to describe the reactions in terms of spontaneity, reversibility, and state functions. All right, so some terms, some vocab for you guys. Spontaneous, which just means changes that occur without outside intervention. Basically, they'll happen on their own. Once they start going, they're going to keep going. You don't have to do anything to keep them going. We also have irreversible, meaning you cannot restore the initial state by simply reversing the process. If you take 2 steps forwards, it's not as easy as just taking 2 steps back. Whereas reversible is a process in which the original conditions for the system and the surroundings can be recreated by reversing the process. Oh, well, I put 5 joules in, just remove 5 joules. That would be a reversible reaction. All right, so spoilers. If a reaction is spontaneous, it is also irreversible. And if a system is in equilibrium, the products and the reactants can interconvert reversibly. All right, so spontaneous means we can't just go back the way that we came from and end up with how we started. That's irreversible. So spontaneous, irreversible. Equilibrium, reversible. All right, so spontaneous reactions have a definite direction. They're definitely going to a product side. It's not unclear where it's going forward. They're also irreversible. So breaking of an egg, definite direction, you drop it, it's going to the direction of breaking. It is also irreversible. You can't unbreak an egg. Same thing with combustion. It's definitely burning and making carbon dioxide and H2O, and you can't go backwards to make the sticks that you started with, right? All right, so here is a classical chemistry example. We have a chamber with a gas separated by a valve. So we have a valve right here, and we got gas over here, and we got a vacuum on the left side. So nothing. There's nothing in here. Not air, not atoms, not anything. It's a vacuum. All right, so what happens when we remove the valve? Well, now this gas that was contained on one side is free to diffuse and move into the other side, which is what it's going to do spontaneously. The gas is going to spontaneously expand to fill the entire container now. No work is done because it is expanding into a volume, or I'm sorry, into a vacuum. So there's nothing there for it to do work on. It just expands spontaneously. Now, if we wanted to restore the original conditions, we'd need this piston to compress the gas back into one side of it and then, close our valve. So if we have to compress the gas using that piston, we're doing work. So we're not able to go back to the conditions that we started with in the same way. We have to do work. No work was done to diffuse out. In order to get it all into one side, we'd have to do work. So different path back means that this would be an irreversible reaction, right? All right, spontaneity, dependence on temperature. All right, so think about this, melting and freezing of ice. You put an ice cube on a sidewalk in the summer, it will occur, melting will occur spontaneously. It's going to do that all by itself. Same thing if you put some water in a freezer, the freezing will occur spontaneously. So here we have opposite reactions that are spontaneous under different conditions. So we know that temperature is going to play a role in our spontaneity. Yep, that's what I said. All right, so reversible processes. Picture the following. You have a glass of ice water at 0 degrees Celsius. Here is your glass of ice water. And right there, that's a better arrow. Anyway, 0 degrees Celsius means that we have an equilibrium between solid and the liquid, from ice into water, right? So we got this equilibrium there. Both are occurring. There's melting and there's freezing occurring at the same time. That's why we have these double arrows. Both are happening. If heat is added, ice will be melted, right? And if we wanted to restore the original conditions and end up with the same ice that we started with, all you have to do is remove the same amount of energy that you put in. So this is a reversible process because we can go back to the original conditions just by reversing the process that we did to it. All right, so reversible, equilibrium, no definite direction, right? We had this double arrow. So is it going to freeze? I don't know. Is it going to melt into the liquid? There's no definite direction. Both are occurring. Yep, non-spontaneous in either direction. Cool. So generally speaking, systems at equilibrium are reversible and non-spontaneous. All right. A side note, Just because something occurs spontaneously doesn't mean that it will occur at an observable rate. We've done nothing to determine how fast a reaction will occur. We're just saying if it will occur spontaneously. Maybe really, really slow, maybe really fast. We've said nothing about that. All right. Just like rusting of a nail. You know, you put a nail on a table, it's going to be rusting. You're not going to be able to observe it, but you come back in a decade or so and you'll see that it has rusted. All right. So pop quiz. If a process is spontaneous, it is also what? Irreversible. 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 Sound it out, Donahue. All right. If a process is reversible, it is also non-spontaneous. I can't spell anything today. There we go. I think that's how you spell things. Anyway. All right, so ice melting at 10 degrees Celsius is an example of a what kind of process? Well, since it's above the melting point, it is a spontaneous process. That's it. That's 19.1. You know, I hope you found it helpful. I'll see you in class. Bring questions. All right. See you there. Goodbye.